So there is only one difference between uniform cost search and A-star search. That one difference is how they sort the priority queue. Uniform cost search sorts the priority queue based on the cost so far of every path. They're all sorted, and whichever path has the lowest cost, that's the one that's going to come out next. A-star search sorts the very same set of paths, but it sorts them based on A-star when comparing two paths, or the state at the end of the path rather, will say, okay, not just how much did each state cost, but how much did the state cost and how much is remaining left to get to the goal. And you sum those two values together and you compare those values. So cost plus heuristic, let's just call that value, is what A-star sorts by, and whichever one has the lowest value is going to come out first. Yeah, so if you just had a multiplier in there and you always multiply the heuristic by 0, then it's uniform cost search. And if you always multiply the heuristic by 1, then it's A-star search. And you could even interpolate between them by tuning that multiplier or something like that, if you wanted to. There's many ways one could do it. But yeah, the only thing you're really supposed to do for this assignment is implement uniform cost search and then make another comparator for A-star search, and then you've done it all. Let's talk about the comparator. I think that's an important thing that caused most of the problems that I've been seeing in the homework so far. Let us compare, how about two numbers? Which is bigger, the number 29 or 31? I know this is a stupid question because I want you to know the answer. We're going to analyze how we know. The answer is obviously 31 is bigger, 29 is smaller, right? But how do you know that? Well, because since first grade, you have been understanding that the first digit is more important and the second digit is less important. And so when comparing these numbers, the alligator goes for the bigger number and eats the bigger number. Therefore, it looks like that. In computer science, sometimes we use little endian instead of big endian. What's that all about? So imagine that we had a whole bunch of numbers that were sorted using a little endian format instead of a big endian format. Would that work? So this number on the left is actually 92, and the number on the right is actually 13. Which one's bigger? If we compare in a little endian format, well, then this is the most significant bit, or digit, and we compare this one first, and then we compare this one. And because 9 is greater than 1, now it's like that. And turns out it doesn't matter. You can have all the numbers in the world, and you can sort them by little endian or big endian and throw them into some set, and they won't stomp over each other because there's still some consistent way to compare them, right? Okay, what happens if you write your comparator like this? Let's suppose that I have a byte arrays and I've stored my digits in the bytes, just for the sake of thinking about it. And I write my comparator to say, if A of 0 is less than B of 0, return -1. If A of 1 is less than B of 1, return -1. If A of 0 is more than B of 0, don't write this down, this is the bad example, by the way. If A of 1 is more than B of 1, return 1. Otherwise, return 0. Or P, whatever makes you feel good. How do you feel about this comparator? What's that doing, right? Are you confused? Well, I've seen a lot of comparators like this as I've looked through your code, and here's what it does. Have you seen your frontier goes out, but then it doubles back on itself, and you have frontier in the middle of cutting through the frontier, and you have thick frontiers, and you kind of have no frontier sometimes, and it blinks and jumps around? Yeah. Oh yeah, that's what I meant for my bad example. Thank you. And just to make it clear, bad, bad, bad. Not that particular line, this whole thing. Just so somebody finds this on the video and starts copying. What's wrong with this comparator? Well, look, we're comparing the first digit, and then we're comparing the second digit for lesserness. Then we're comparing the first digit for greaterness, and then the second digit for greaterness. What happens if we sort numbers that way? Well, is it consistent? it depends. When you imagine yourself building a tree and you start to build the tree, well, first the 29 goes in and the 31 goes in, and it's going to go on one side of the 29. But you put in another number, and depending on whether it's, say, 50 or 59, let's pretend that was a 28 so I can be bigger or smaller. Do you see how that's going to make a difference as to which side it goes on? And yet it shouldn't, because this is the least significant bit. And so ultimately what I'm saying is this comparator will not make a consistent tree. Your set will fail to find states that it should have found, and so it basically doesn't know where it's been before. And that causes a uniform cost search to fall apart. By contrast, if our comparator simply does this, where we check the first digit and then we check the second digit, and then we return 0 if they're all equal. Do you see how this is the same thing you do when you compare numbers? Okay, and let's suppose we do little endian instead of big endian by swapping the order. Oops. Is this okay? This is okay too. So this is a valid comparator. You don't have to check the first digit and then the second. You can check the second digit and then the first. But you can't check for lesser than and then greater than together. You have to check the lesser and greater than on the first digit and then on the second digit, or vice versa. Otherwise, you get all kinds of badness. Kind of like when comparing numbers. We know how to tell which number is bigger, right? It's hard to tell immediately. You'd have to count the number of digits. But if they're the same, you'd start comparing the most significant bit, and you'd run down until you find the others. And note that you don't need to vote. We don't need to say, okay, well, 9's bigger than 1, so this one's probably bigger. But then again, 7's bigger than a 2, so maybe the other one's bigger. It's just whichever, as you do some arbitrary order, whichever one trumps dominates, right? And that's what you need to do in writing your state comparator. And that's not the same thing as your cost comparator, and keeping those two things straight is pretty much the crux of this whole problem. Yeah?
When you're comparing states, do you mean comparing the XY position, or?
Yes. Sorry, that was an analogy, a metaphor I never finished. A1 means X. We'll say state.x. And B1 means state2.x. Yes, basically by A I meant X and by B I meant Y. Remember in assignment 1, I wrote the comparator for you and I looped through all 22 dimensions, and in each dimension I first compared for less than, then I compared for greater than. So people that were careful in maintaining the same code in the comparator wrote it like this and it worked. And people that didn't quite know what they were doing wrote a hybrid mess that didn't find the same. Basically what happened is your states got sorted in the tree in a way that wasn't consistent, so it couldn't find states when it was looking for them, and it kept thinking you hadn't been there, and it kept exploring places it had already been. So a lot of people were checking for exact equivalency in their have I been there yet set, and with floating point numbers it's pretty darn important to check if you're within a range. So you could write a distance equation, right, and compute the math dot square root of a.x minus b.x, and then you could say if that is less than, say, 10, then you're on the same state, right? But why do all of that math work when you could just say, if you have state.x, all you have to do is say divide it by 10. So now you've taken your floating point position and you've reduced it by 10, and then cast it to an int. And now you can say if that is equal to int of state2.x divided by 10. And do you see how this basically is comparing, it's saying, are you in the same square on the screen? So you've got two floating point numbers, and they may be off by a distance of 9, but it's still going to say, hey, they're the same, because when you divide by 10, that moves it into the decimal point. When you cast to an int, that drops the decimal place. And so this will check within the region of the square. And this kind of comparison was pretty important to be able to do in that assignment. Some other gotchas. Let's see. This was a big one. Another huge one involving this divide by 10 thing was Remember how the difference between A star and a uniform cost search is that you add the heuristic, right? Well, a lot of people didn't quite notice that when they were stepping through the states in uniform cost search, they were taking steps of size 10. And then when they were measuring the distance for the heuristic, they didn't divide by 10. You see what that would do? Basically, their heuristic was 10 times bigger than it was carrying 10 times the weight of the cost so far. And so they weren't just doing cost plus heuristic, they were doing cost plus 10 times the heuristic, or 1/10 the cost plus heuristic, however you want to put it. What does that do to your results? Yeah, so it overemphasizes the importance of the remaining cost, and so it basically turns the algorithm into a greedy search. And essentially, people that did that will see a frontier that tightly bounds your path all the way straight to the goal, and it finds a not intelligent path. So,
what if the path is really square for some reason?
Really square path. You mean the frontier is really square? Here's another problem that keeps on occurring. People keep adding the heuristic to their cost, and then when they are at a node and they branch off to the child node, they clone the parent and add the cost to the child, and now they add the heuristic again. Do you see what's happening? They're double dipping. The heuristic is going to be compounding exponentially, whereas the cost is just going to be growing normally. And then what ends up happening is the heuristic has way too much strength, and again, that'll make it turn into greedy search because it just focuses on the remaining cost and never on the cost so far. So that could be it. My advice as far as this goes is only store the cost in the node. The heuristic, just compute it when you need it. And the place to compute it would be inside of the comparator. I want the lower cost. If a.cost is greater than b.cost, return 1, otherwise return 0. This is an example of a comparator for uniform cost search. Are you with me? Assuming that every state has a cost in it, and every time you create a child node, you're going to have to spawn that child node, copy the parent's cost, and add to it the cost of taking a step from where you're at. And you remember, of course, cost is the reciprocal of speed, right? Don't just use speed, otherwise it searches for the worst possible path instead of the best possible path. If your path is going straight to all the lakes, you're using speed as cost. You do also have to multiply by distance, although it kind of doesn't matter if your distance is uniform. So you do have to multiply by root 2 if you're going diagonal, and 1 if you're going straight. Or if you wanted to be more formal, you'd multiply by 10 going straight and 10 root 2 if you're going diagonally, right? Okay. And then when you add the heuristic, you won't have to divide by anything. So let's now do the heuristic. I'm going to pretend I know these things. I'm just going to add into here plus distance between A and goal, and plus distance between B and goal. And before you panic, I'm not quite done yet, but I will be very soon. There, I have now turned it from uniform cost into a star search, except distance is not a very good heuristic because it's not really the distance, it's the distance times the terrain that you're running on, right? As it happens, the lowest cost space in the map has a cost that's less than 1. It's something like 0.1. So if you neglected to multiply, probably less than that, if you neglected to multiply by the lowest cost square on the map, then this heuristic right there would overwhelm the computation, and you'd get basically greedy search, or at least too greedy of a search. So what we really need is distance times lowest cost times low cost. Oh yeah, and let's suppose we have a float lowest cost, where lowest cost is some value that I computed that's the lowest cost of any square on the entire map. A.cost, how was that computed? Did you, every time you take a step of size 10, just add the cost of that one square you're on? If so, then the cost you were thinking about in your head when you did it was that it only costs 1 unit of cost to get to 10 spaces away, right? Therefore, when you compute distance, you better compute it the same way. So basically what I'm saying here is don't get confused between the two spaces, right? You could call these coordinates 0, 1, 2 if you want, or you could call them 0, 10, 20 if you want, right? And it doesn't matter what you do, but just don't confuse yourself and be inconsistent. If your cost for starting right here and going bing, 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 if that was a cost of 20, because you did 10 to get from here to there, plus 10 to get from there to there, then you're counting them on a pixel basis, right? Then, if your goal was, say, this square up here, and you just measure the distance like that, then you've done it correctly. However, if you say that the cost of starting here and going there and then going there, if that cost is 2, or 2 units times the cost of walking on that terrain, and then you add to that a distance here of square root of 2 times 10, do you see what's going on? You're putting too much emphasis on the heuristic. Now, can you just take this value and divide it by 10? What we really need to do is we need to take these differences and divide those by 10. And now what we've done is we've actually computed a distance in the new domain, right? Because now we're saying that this yellow line will be counted as exactly square root of 2. And if you calculate the distance that way and then multiply that by the lowest cost square, then you've got the correct heuristic, and this will add up to doing the right thing. These are real problems. This is the kind of stuff you face when you take AI and you try to use it. And that's really, you know, it's one thing to teach people a bunch of tools that they can never use for the rest of their life, and it's quite another to basically force them to confront real-world problems. You have to, in the real world, connect these algorithms, these ideas of searching, with real spaces. Diagonal moves versus horizontal moves are a real thing that come up all the time. So you needed to know how to handle that. I think that the idea of having a non-uniform terrain comes up a lot. I think that the notion of knowing how to balance between distances and costs is important. All of these are pretty important principles. I also think it's important you can write your own comparator, because the world doesn't just do that for you. You need to know how to put stuff into a set and say, have I been here before? And the idea of discretizing your position to avoid, so you can detect when you're in a position you've been to before, that's kind of real world too. So I guess what I'm saying is, I know these instructions are kind of bad, and it was kind of entirely on purpose because I wanted you to struggle, and you did, and I feel happy about that, and I'm sorry, but not really. However, it was just due yesterday, and you know how I don't take off that many points, and now I've told you all the secrets to this assignment, so now you can all go fix your bugs and get it taken care of, right?